In this presentation, I am going to describe QBP, which is a flexible framework for querying business process models. My name is Sherif Sakr. I am from the School of Computer Science and Engineering, University of New South Wales, Australia. This is a collaboration work with Muallim bin Atallah and Ahmad Awad from Hasso-Plattner Institute on University of Potsdam, Germany. By definition, business process is a set of coordinated activities which is designed to achieve a specific business objective. Business process modeling is a complex and time-consuming task. To design a process model that needs to define the activities that needs to be performed, the order of their execution, handling and how to handle the exceptional case that might occur in this business process. With the rapid growth in the number of process models, a framework for reusing previously designed business process models is of a great practical value. When we speak about querying and reusing, we are in a direct need to a query language which can help the users to express their queries. The Business Process Management Initiative has developed a standard business process modeling notation called BPMN. In our framework, we rely on a business process query language called BPMNQ, which is a visual language that relies on the notations of the BPMN language as its concrete syntax. BPMNQ is used to query business process models by matching a process model graph to a query graph. BPMNQ extends the set of notations of BPMN with 7 new elements. Some of these elements are flow objects and the others are for connectivity. The first object of BPMNQ is a variable node, which is used in the query to indicate unknown activities to be pointed to this variable node. The second construct, which is the generic node, which indicates unknown node in a process. Generic split object refers to any type of split gateways. Generic join object refers to any type of join gateways. The negative sequence flow object states that two nodes A and B are not directly related by sequence flow. The path object states that there must be a path from a node A to a node B in the target business process model. The negative path object states that there should be not exist any path between two nodes A and B in the target business process model. Actually, there are so many different use cases for querying and reusing business process models. The first use case is to provide the business process model with a lookup functionality for retrieving their process models. It also helps in reusing, redesigning, or improving existing process models. It also helps in detects anomalies in process model by detecting situation where deadlocks can execute or where any process instance is not compatible with its defined process model. So it's used for validating process model against superordinate specifications. Also, it is used for identification of equivalent and similar processes. The architecture of our framework consists of 6 main components. The first component is the translation middleware. This component translates the business process model from specific language syntax to the proprietary internal representation. So this middleware can translate models from the Babel language, Xlang, UML activity diagrams, or ABC notation. The second component is the relational business process repository, which is a central database that stores an abstract uniform representation of the enterprise process model. Conceptually, business process models are represented by graph data structure, where events, activities, and gateways represented by graph node, and the sequence flow between any node, two nodes is represented by an edge. On the physical level, we use a fixed mapping storage scheme to map this graph data structure into a tabular relational representation. The business process designer uses the BPMNQ query editor component, which is a web-based visual editor where the business process designer can compose their queries using the BPMNQ notation. After composing this query, the semantic query expander component receives this query and tries to analyze the labels of the activity in the process query to determine from the semantical point of view and derive a list of semantically similar activities to the activities of the input query. The query processor receives the BPMN query graph and translate this BPMNQ query into a sequence of SQL scripts, which is then shipped to the back-end relational database management system. The query processor receives the result of these SQL scripts with the candidate set of business process models and verify each of them against the query condition and return the set of result process models to the end user. The end user can view the result business process models using the model editor component. From the database perspective, BPMNQ query can be considered as a graph query problem, as the BPMNQ query is used to query business process model by matching a process model graph to a query graph. However, the query processing of BPMNQ queries is more challenging, and goes point the traditional sub graph query processing in two main aspects. The first aspect is the BPMNQ query don't treat all nodes of the graph repository or graph query in the same way, so each node have its own type and its own characteristics. So one node can be activity, one node can be a gateway, one edge has a specific characteristic and the state and so on. At the same time, the connection on the edge between the nodes of the subgraph query is not always simple or direct connections that can be evaluated using the intuitive retrieval mechanism. So these query edges can represent more complex and recursive types of connections, such as passes, negative passes, and negative connections between the nodes of the query graph. Therefore, we need to apply an efficient and filtering and verification techniques to achieve an acceptable performance for such challenging queries. The backend the backend query processor of our framework is using relational database technology. The main reason of this choice that the relational database have shown its ability to handle vast amount of data very efficiently using its powerful index structure. And to avoid the high cost of evaluating BPMNQ recursive constructs such as pass constructs, negative passes, and negative sequence flow, we divide the task into two phases. Filtering phase, where we use the structure of the query graph to retrieve the minimum set of candidate process models, and then we verify each candidate process model against the query graph to check if it satisfies the query conditions or not. We also employ a novel decomposition-based and selectivity-aware translation mechanism for processing the BPMNQ query. We use a statistical model to influence the relational query optimizer by some optimization decision to find the most optimal execution plan on the back end. To find in the project page, we have uploaded a video tutorial to describe how you can use our web-based query editor to design, build, execute, and evaluate BPMNQ queries. To find more details about our project, please visit the project page on the SourceForge website, ppmnq.sourceforge.net. You can also visit our online demo page, and for questions please contact Sakr at cse.unsw.edu.au or ahmad.awad at hpi.unipotsdam.de. Thanks for your attention.